We have been doing some experiments in the last few years where we've been looking at how water interfaces with the surface through this single layer of graphene. And in this talk, I want to share with you our experiences in this area. So to give you some background to this talk, there is a great deal of interest in graphene coating. One can deposit graphene on copper, one can do it on nickel, one can control the number of layers, single layer, bi-layer, tri-layer, and so on and so forth. And so this is becoming more and more routine now. And these kind of coatings have some very nice applications. For example, in terms of blocking oxidation of surfaces. So if you have a very high quality coating, which doesn't have defects and so on, then not even a proton can pass through it, right? So you can completely passivate the surface. So for example, if you take a block of copper like this, and you have no graphene and you heat it at high temperature in air, it's going to oxidize and rust like this. Whereas if you take the same graphene coating and you coat it with, if you take the same block of copper, you coat it with graphene and heat it, it will not. So, these kind of surfaces have a lot of applications. And, we thought, let's ask ourselves a very fundamental question. And that is, if people are going to build these kind of coatings, how does water interact with this type of graphene coating? So it's a very fundamental question. It's not driven by an application or a product or anything like that. But we just want to know this thing, that how is water going to interact with this type of coating? Before I address that, let's take one step back and say, how will water interact with a graphene with no substrate? So let's say I have a freestanding graphene sheet like this, no substrate, nothing. How will a water drop interact with that sheet? And so people have done modeling of this, and based on MD, you can calculate this contact angle theta, and the contact angle sort of tells you if the surface is hydrophobic or hydrophilic. If the contact angle is very large, that means the surface is hydrophobic in the sense that the water does not like the surface. If you get a very low contact angle, it means the surface is hydrophilic, right? So you can use this value to say is the surface hydrophobic or hydrophilic. And so what people have found is that, so there's this paper in Langmuir which came out recently which said that if you take a single graphene sheet, the contact angle that you get is about 102 degrees, okay? Anything above 90 is hydrophobic. So according to this paper, a single sheet of graphene is strongly hydrophobic. But now when you go to graphite, people have measured 90 degrees, and these guys also get 90 degrees. So when you add the second graphene layer, so if you take bi-layer graphene, the contact angle drops from 102 to this value. You take tri-layer graphene, 3 layers of graphene, it drops further, 4 layers, 5 layers, and 6 layers, then it's sort of stable over here. So what these guys are showing is that it's not a pure surface effect. It's not just the top graphene layer, because if it was only the top graphene layer that was influencing the contact angle, then the first layer itself should have given you 90 degrees. But the first layer is giving you something much greater than 90 degrees. It takes several additional layers to get this down to 90 degrees. That means water is influenced by the underlying graphene layers. It's not just the topmost layer. The second, the third layer has some influence on the contact angle. There's also a paper that also came out recently where they made Janus graphene. So Janus means two-phase, right? So on one side of the graphene sheet, they use one type of functional group. On the back side, they use a different type of functional group. And what they found was that if you have a functional group only on one side, and this functional group was actually hydrophilic, they got a very low contact angle. Now, as they functionalize the back side with the hydrophobic group, the contact angle goes up from 30 degrees to about 60 degrees. That means even though the water is not in direct contact with what is going on at the back side, it is influenced by what is going on in the backside. So as you functionalize the backside, the contact angle on the top side changes from 30 degrees all the way up to 60 degrees. So water can, in a sense, look through, at least partially look through and sense what is happening on the backside of the graphene sheet. So inspired by these studies, we said, let's do our own experiments. And so what we did is we took surfaces like silicon and gold, and we coat it with a single layer of graphene. And we measured the water contact angle with no graphene and with graphene. And what we found is that there wasn't much change. So if you look at silicon, you go from 32 to 33. If you look at gold, you go from 77 to 78. But no big change if you just use one layer of graphene, which means the substrate it appears to dictate the contact angle rather than the topmost sheet of graphene. We then looked at things like the advancing and receding contact angle, because the static contact angle is one measure of how water wets a surface, but you also need to look at advancing and receding contact angles. So when you measure advancing contact angle, what you're doing is you're increasing the volume of the liquid drop. So the liquid drop is spreading like this, and this now becomes the advancing contact angle. And in this case, silicon gave us 36 degrees. The same silicon with the graphene gave us a little bit lower value of 35 degrees, but no big change in the two cases. If you look at the receding contact angle, where what you're doing is you're taking the water drop out, so the volume of the liquid drop is shrinking, and so the contact line is moving this way, and this is the receding contact angle. For silicon it was 30, with one layer of graphene 31. Again, no big difference, a small change, but no big difference. So again, it appears that the substrate has a very profound effect on the way the water wets the surface. So then we moved over to copper. And on copper, again, the same thing. This is baseline copper, and you put one layer of graphene, not a big change. Then you put two layers of graphene, 3, 4, and then after about 6 layers, there was no change. So it kind of stabilized at the value for bulk graphite. So bulk graphite, typically people measure around 90 degrees. And that's what we get for 6 and more layers. Right? So there's this gradual transition in the contact angle till you get to about 6 graphene layers. After that, it behaves just like graphite, right? So beyond 6 layers, it's the same as graphite, no change. Okay, so we sort of wanted to understand why this is happening. And because normally in surface science, people believe that the wetting is dominated by the skin. There isn't a very strong depth effect. So in this case, we are seeing a sort of a very significant depth effect. And to sort of understand that, we first use MD simulations. So we take a surface of copper, we have a water drop on it, and we can measure the contact angles. Then we take the copper with one layer of graphene. We take the copper, we put in 2 layers, 3 layers, all the way up to 6 layers. And in each case, we can find the contact angle. And what we found, and this has more details are there in our paper. But the main point is that we saw the same type of transition in the wetting as you go from water and copper to water and graphite. Keep in mind that these values from MD of 84 degrees and 90 degrees, this was obtained by actually fitting the MD to the real experimental data. So we actually matched the binding of water to copper and water to graphite to make sure that these values were reasonably close to what we had in the experiment. And then we added 1 graphene layer, 2 graphene layers, 3 graphene layers, 4 graphene layers, and you see the same gradual transition in the contact angle from pure copper to bulk graphite. So experimentally and in terms of the MD simulations, we see qualitatively at least the same behavior. So why is this happening? So this is our hypothesis, which is that if you look at any perfectly clean metal surface, like for example copper, if it is perfectly clean, there will be actual chemical binding between water and the metal surface, and the water will be completely hydrophilic. It will spread completely on the surface. But in practice, there's always a passivation layer that forms, which is a very thin oxide layer, and this passivation layer forces the water to interact with the metal surface through the van der Waals interaction. So you don't get direct chemical bonding anymore, you don't get hydrogen bonding anymore, you get the van der Waals interaction between the water and the substrate. And those are much weaker interactions. The van der Waals force are much weaker, and that drives up the contact angle. That's why the contact angles are much higher. So this is what happens on a regular metal surface that is passivated. Now, when we grow graphene, what happens is before we grow graphene, we pass hydrogen at high temperature over the substrate. So it completely removes this passivation layer. And instead of the passivation layer, we now have the graphene layer. So the graphene layer, in a sense, is replacing the passivation layer. And graphene is now the new passivation layer. This now acts as the new passivation layer. And it does exactly what this does, is it forces the water to interact with the underlying substrate through the van der Waals interactions, which are very weak interactions. And in that case, for example, this water will see all of these coppers, and pretty much this water here also sees all of these coppers. So we get a very similar contact angle in the two cases. Now, when we add additional layers, what happens is we force the water to go further and further away from the substrate. You see less and less of the copper atoms. You see more and more of the carbon atoms. And so the contact angle starts to transition towards the carbon value. When you get to six graphene layers, you see only carbons. And now you start seeing the contact angle of bulk graphite. So this is our hypothesis, and we've also done some classical modeling apart from MD, and here what you do is you define this WH term, which is actually the solid liquid, which is basically the work done to take two surfaces. So for example, if I have infinite water and I've got infinite copper, this is the work done to bring these two surfaces from very far away to a certain gap H, right? And if I know what this is, W, I can find the contact angle theta. Now, assuming that there's no chemical bonding going on between water and copper, I can express this in this 12-6 form, where one term sort of captures the binding of the surface, and if you bring them too close, obviously they're going to be thrown apart, right? So you have these two terms. So if I assume that W is in this form, I can express, so we have water and copper, but we've got this thin sheet of graphene in the middle, so I can express this as W water copper at a spacing H plus D, correct? And I can model the graphene sheet by subtracting out this term from this term. So W of water on graphite, bulk graphite at spacing H, minus water on bulk graphite at spacing H plus D. If I subtract these two terms, I should get the effect of this very thin graphene layer, right? So I have these two terms here. If I add this, I get an expression that looks something like this. Now, keep in mind here that the constants A are actually known for like water and graphite and water and copper. These are known values. D is my unknown, right? And the constants C and H I can fit because I know the experimental value for water contact angle on graphite and water contact angle on copper. Since I know those experimental values, I can back calculate what these C's and the H's are. So my only unknown here is D. So so I can sort of vary my film thickness, and by varying the film thickness, I can back calculate W, and from that I can get the contact angle theta. This is a very simple model. It runs very fast. You don't have to use MD, but it captures the same trends. So this is again the water on copper. This is water on graphite. This is what I get from the MD simulation, and this is what I get from this very simple classical model. And it shows again the same kind of wetting angle transition from the copper value to the graphite value. And here, after about 4 layers, I don't see any effect. Here also, after 4 layers, I really don't see any effect. In the experiments, it took about 6 layers, after which I did not see any change in the contact angle. I would say the MD is closer to what we see in the experiment compared to this simple classical model, and that probably is because the MD actually captures the atomic level discreteness of the film, right? You're sort of modeling it atom by atom, whereas here, you're only assuming a certain film thickness. So you say, okay, the film thickness is 0.5 nanometers, 1 nanometers, 2 nanometers. You're really not modeling the film atom by atom. So this is much more accurate and much closer to what we see in the experiment. Now, I just want to give you an example of where you see this effect being extremely powerful. So this is some work we did with this group where we made graphene and we transferred it on a hole. So this is actually a silicon wafer, and it's got holes in it like this. And if you transfer the film on it, this part here has got no underlying substrate. So this has been opened here to show you that there is no underlying substrate over here. And here you got silicon, right? And so the same graphene sheet extends over the hole and then goes onto the wafer, the silicon wafer. So we put this inside a environmental SEM, and we actually cooled the surface. So we cooled the surface down until you start getting phase change. So you start seeing actually liquid drops that form, right? And what you see is that the part that has graphene with no substrate, right, is very hydrophobic. And there's almost no water that forms over here. There's this one liquid drop that I can make out, but there's hardly any water that forms on this surface. But the same graphene sheet, when it extends over the silicon wafer, you see this tremendous amount of water that has formed over here. So the same graphene sheet here is hydrophobic. The same graphene sheet here is strongly hydrophilic because it's being influenced by the underlying silicon wafer, and we know silicon is very hydrophilic. It has a contact angle of 30 degrees. So the same graphene sheet, when it comes here, now behaves as a hydrophilic material, but with that same graphene sheet is here, it behaves as a strongly hydrophobic material. So it's a very powerful example of how the underlying substrate can essentially change the way the film behaves. Now, the next question is that, do I need graphene? Can I have any other very ultra thin coating? Will I see the same effect? So we found that actually people have observed similar wetting angle transition that we are showing. People have observed that before. For example, people have looked at the wetting of polymers on silicon, and they have seen exactly the same transition where when the SiO thickness is very low, you start seeing the contact angle of PS on silicon. When the SiO layer becomes thicker, you start seeing the contact angle of PS on SiO. So the same transition behavior people have reported before. And here the SiO layer can be pretty thick. It can be about 5 nanometers thick. So you don't, the point is, do you really need to go to the extreme thinness of graphene? Well, it turns out that for water, you need to. Polymers like PS, they are long molecules, they have a long range of interaction. So the van der Waals range is much greater. Water has a very small van der Waals range, and with water, you certainly need to be ultra thin. For example, this is copper, this is graphite, right? If I put one layer on copper, I don't change much if my thickness is the same as one graphene sheet, which is 0.34 nanometers. But suppose the carbon layer was thicker. Instead of 0.34, let's say it was 0.7 nanometers. Well, the contact angle would jump up here. If it was 1 nanometer, it would jump all the way here. You would completely lose any kind of transparency. So in the case of water, the van der Waals interaction range is very small, and you need an ultra thin coating in order to see this transparency effect. Even if you're like 1 nanometer thick, you're not going to see this effect. And that's really why graphene is special in this case, because there's nothing that can rival thinness of graphene. Maybe HBN can, but hexagonal boron nitride is very difficult to sort of deposit over large area substrates. But with graphene now, people have things have improved to the point where we can do large area roll-to-roll deposition of graphene. So I think the extreme thinness of graphene does make it special in this case. Of course, it's also mechanically very stable. It's strong and flexible. And it's also not likely to oxidize away, which is important when you're using water as a wetting liquid. So it's got a whole range of advantages. So we have a paper on this that came out recently. This has more details. You can read that for more information. Okay, now when we wrote this paper, we really didn't explore the full range of contact angles, and it turns out there are definitely ranges where the wetting transparency breaks down. And one case where the transparency breaks down is on a super-hydrophilic surface. So let's say I have a surface like glass. Now glass is super-hydrophilic because you get hydrogen bonds that form between water and the substrate. Now these hydrogen bonds cannot form through the graphene sheet. So if I put a layer of graphene on glass, these hydrogen bonding networks are now broken. And so the contact angle jumps up. So for example, the clean glass is here, one layer of graphene jumps it up quite a lot. So the wetting transparency effect is completely lost on surfaces where the wetting is dominated by chemistry, which is hydrogen bonding networks forming. Because these networks cannot, for example, form, these kind of chemical bonds cannot form through the graphene sheet. Also, it breaks down on a super-hydrophobic surface. So this is a paper that came out last year by the Strano group at MIT. And these guys repeated our experiments, right? So what they did is they took a range of different surfaces, and this is the contact angle with no graphene. This is the contact angle with graphene, okay? If these two are equal, if you have transparency, then the contact angle without graphene and with graphene should be equal, right? So the transparency line should be this line. Okay? And for this surface, they're close, this surface, they're close, But if you look at these surfaces, you start to deviate completely, right? So it follows the transparency line till this point and then, leaves completely. And that's because the maximum contact angle that you can achieve on a graphene sheet is about 100 degrees, right? So if you go beyond, if your underlying surface is more hydrophobic than graphene, right? So the graphene value is 100. If your underlying surface is 150 degrees or 130 degrees, then the graphene will take over the wetting. The underlying surface has a very minimal impact when it's less wettable than the graphene surface. That's why you max out at this 100 value. So it's very close to 100. You max out at the 100 value, and then the graphene takes over the wetting behavior. The transparency only applies when the underlying substrate is less wettable than the graphene. Sorry, if the underlying surface is much more wettable than the graphene, then you see the transparency. Okay, also, there are issues with growth. If you don't grow it well, the substrate is too rough, then the problem is that the spacing then increases and then you won't see the effect. Also, the transfer is very important. If you do a bad transfer and there's too much junk on the graphene surface, obviously, that's an issue. So you have to be very careful with how you make these samples and how you transfer them. Now, beyond flat surfaces, we've also looked at rough surfaces. And here's an example of a rough copper nanorod surface. And we coat it with graphene like this. And this is like a graphene drape, right? And the question is, what does graphene do to the wetting behavior of this surface? So obviously, it will not give you wetting transparency because this underlying surface has entrapped air pockets. It's very hydrophobic. And the graphene is actually less hydrophobic than this surface. So the graphene wetting will take over, obviously. So you don't see transparency. But when you do impact of water droplets on this, so for example, I take a surface like this and I impact it with a water drop, because the drop hits the surface with some energy, it forces itself into the surface, it displaces these air pockets. And you go from the Cassie state where the drop is floating on the top, you go into so-called Wenzel state. Right? And when that happens, for example, the drop hits, it spreads, and it actually penetrates into the surface, displaces out all the air pockets, and then it gets stuck. So if you look at the contact length here, the contact length here is not changing. That's because the droplet hits the surface, spreads, but then it's not able to recede, right? And so it's essentially stuck to the surface. So the contact line gets pinned over here. Okay? So this is a big problem on range of rough surfaces. It's very difficult to move water drops if this happens. Now you put the graphene drape on there and you impact it, you see the same behavior. It spreads, but this time the contact line is free to recede. You can see it sort of recedes and goes back. And in fact, you can plot this out over a size scale is about 1 millimeter. So the drop size might be about 1 millimeter. Because the graphene films, we grow inches in size. So when we transfer them, it's like 1 inch by 1 inch. So, we can always drop the drops anywhere on the surface. And if you plot out, for example, the non-dimensional contact line length. So take this length and divide it by the final length of the drop. So that gives you the non-dimensional contact line length. So you plot that out, and you find that with no graphene layer, the drop spreads, but then it gets pinned, right? It goes into the surface, gets stuck to the surface. This remains constant, does not change after that. But you put even one layer of graphene, and now it spreads, it retracts, it spreads and retracts. So the contact line is free to slip and slide on the surface, right? It's not stuck to the surface anymore. And so the damping here is much lower than in this case. Almost factor of 10 times change in the damping ratio. So there's much less friction on the surface because of the graphene. And actually from the MD simulation, you can even get that. So if you take a surface like this, and the water actually goes into the surface, so it goes from the Cassie state into the Wenzel state, and now you try to slide this drop. So we try to move this drop this way. This now is called the advancing contact angle. This is now the receding contact angle. And you see a huge difference between the advancing contact angle and the receding contact angle. This is much higher in value. This is much lower in value. And experimentally also we see something like this. And this is because the fact is that now you've got a lot of friction on the surface, and to sort of balance that friction force, the drop acquires this shape with the fact that the advancing angle is different from the receding angle. Now you take the same drop and you put this one layer of graphene, and now you move the drop at the same velocity. So in both cases, we're moving the drop at the same velocity. This case, the advancing contact angle and receding are almost the same. That means there's no hysteresis. There's almost zero contact angle hysteresis. And the hysteresis sort of gives you the friction force. So in this case, the friction force is almost zero, which means the drop is free to slip and slide on the surface, right? And the friction force here was non-zero, whereas in this case, the friction force is pretty much zero, right? So one can definitely tailor the dynamic properties of water drops on surfaces by using these kind of graphene coatings. So we have a paper on this that just came out in ACS Nano, which has more details about that. So the main points that I want to make are that because graphene is so thin, it can allow crosstalk across the graphene sheet. So if I have two media on both sides of the graphene sheet, there can be crosstalk of the van der Waals interactions across this ultra thin 1 carbon atom thick sheet, right? And that kind of crosstalk is nice, because then what can happen is that the way water wets a surface can be dictated to a certain extent by the underlying substrate rather than this graphene skin. Of course, this effect does not apply when you look at a super-hydrophobic surface, because on a super-hydrophobic surface, the graphene is the graphene surface is more sort of likes the water more than the substrate, so the graphene takes over. On a superhydrophobic surface, you will not see this. On a superhydrophilic surface, also you will not see this, because here any kind of hydrogen bonding networks will be broken by the graphene sheet. And the graphene drape, if you apply it to like rough surfaces, you can sort of prevent water drops from getting pinned or stuck to the surface, which is also quite useful. I'm going to quickly thank my students who've done all the work, and of course the sponsors. And I want to end with one last slide, which shows that sort of there's one new sort of twist to the plot. So this is a recent paper that just came out in Nature Materials, where they show that there's an aging effect for graphite as well as graphene. So if you look at graphite contact angle, 91 degrees that we measure and most people measure is what these guys also measure. But this is after about 1 day. If you freshly cleave graphite and measure the contact angle, it's about 65 degrees, right? So what these guys are saying is that people always assume graphite contact angle is 90 degrees. And that is true after the aging process. But if you have a perfectly clean graphite surface, the contact angle is much lower actually. This change is because of a thin hydrocarbon layer that forms. So the ambient always has some hydrocarbon in it. That hydrocarbon sort of forms a very thin layer on the surface of graphite, and that is what actually causes this aging. The same thing is true for graphene on copper. So you take single layer graphene on copper, this is the final value after about 1 day. And this is what we also measure, because the experiments we did was after about a few days. So these guys get the same value that we get, but immediately after you grow the graphene in CVD, you take it out and you immediately measure the contact angle at time t equal to 0, and you get something like 40 degrees. And then over time it increases until it stabilizes at this value, which is what you get after the aging process is completed. And this is because of that thin hydrocarbon coating that forms, which also forms on the graphene. So these values, the final values that these guys measure, is the same as what we measure, but there's a whole transient involved, right, which we hadn't picked up, which these guys are showing. But the thing that's interesting is that they're also showing the very strong effect of the underlying copper substrate, because if the copper substrate was doing nothing, then this one layer graphene should have also given you a contact angle at least equal to that of graphite, right? But the reason why it drops so much to 40 degrees is because of that underlying copper substrate, which is much more hydrophilic than the sheet of graphene. So again, the fact that you have this transient is quite interesting, because it's something that we had also not realized, that you have this transient that's involved. So that's all I have. Thanks.